we continue to talk about specifications with the state of OAuth, the OAuth de facto standard that we all know about, at least we all use. And for that, we will have a talk from Aaron Parecki, but it will be a recorded talk because Aaron Parecki is in another time zone, but he's the only one maintainer, the main maintainer of the OAuth specification. So we really wanted to be sure we have the story from him. So yeah, I will ask the talk to be
senior
played.
security architect.
Yeah, and we can start
at
the
Okta.
talk.
I'm super excited to be here and talk about the state of OAuth. You might be familiar with OAuth from its use in buttons like these, signing with Facebook and signing with Google and that kind of thing. But is that really what OAuth is? Turns out the answer is yes and no. And I'll give you a little background about what OAuth is and where it came from before we get into some of the more advanced uses of it that we'll be talking about it at the end of this session. Originally, before OAuth existed, this was a very common pattern on the internet. An application like Yelp, when it would first launch, it would ask to find your contacts in order to see if your friends were already using the service. And to do that, it would ask you for the email address on your account and the password to your email. Now we look at this now and we would think, well, I would never give my email login to a random app like Yelp. But this was a very common pattern, and even Facebook was doing it. It's obviously not a good idea to give my Google email password to an application like Yelp because it can access everything in my account, not just the contacts. So ideally what we're looking for is a way to let the application access the contacts that I'm trying to allow it to access and not let it access the actual things in my email. So it's this sort of idea of delegated access, of accessing a limited amount of data in an account that was really the origins of OAuth. I like to think of this analogy of checking into a hotel, where you go to the person at the front desk, you show them your ID and credit card, they give you back a hotel key, and you take that hotel key to the door, and the door opens up and lets you in. Now, in order for this to work, the door does not actually care about who you are. The door doesn't need to know your name or even a user identifier. The door just needs to know, does this key card let me have access? That key card is key to the idea of delegated access. You don't get access to every room in the hotel like you would if you had the skeleton key for all the rooms. You only get access to certain resources in the hotel when you check in. So this makes sense for the third-party app use case. But what about first parties? When the app you're logging into is the app that belongs to the API that it's trying to access. It would be kind of weird if, for example, when you logged into the Twitter mobile app, if it asked for permission to access your Twitter data. But there's a little bit more to it than that. In the first-party app use case, you might expect to see a sort of native login dialog like this in a mobile app. And then when you log in, it would just type your password into the app and that's it, right? Well, what if you then wanted to add multi-factor auth to that application? Whether that's push notification based or SMS or TOTP or any of the sort of two-factor auth methods. You could build this into the app and have the app do what it takes to make that work. But what if you then had 4 different apps that talk to different parts of your system? Now you're going to have to replicate this to all the different applications and duplicate all of that work, adding multi-factor to each of the apps. And there's yet another aspect of this which is even harder to solve, and that's on the user expectation side. Here's an example of a service that actually does this extremely poorly, and that's Apple. Pay attention next time you use an Apple product, how many different looking dialogues in different places you're asked to enter both your Apple ID as well as your Mac system password. And then try to explain to somebody how to identify when one of these dialogues is fake. It turns out it's nearly impossible to describe how to identify real dialogues, which basically means you never really know if you're being phished and if something is trying to steal your Apple password. It's even worse on an iPhone because the dialogue that pops up can be replicated by an application exactly. The dialogue on the left is a real prompt where the phone is asking for the iTunes password, and the one on the right is a fake dialogue that this game popped up asking for the iTunes password, and they look identical. So great, how does this relate back to OAuth? Well, OAuth was originally created to solve this third-party app use case of, I don't want to give Yelp my Google password, but I want to let it access data. And it turns out that that same mechanism can also solve these problems with first-party applications. It's all based around this idea of starting at the application and then leaving the application, getting sent to the OAuth server, doing your authentication and multi-factor there, and then returning back to the application where you're then logged in. So for the third-party app use case, this gives us an opportunity to prompt the user to ask them if it's okay for this application to access certain amounts of data. And in the first-party app use case, this gives us the opportunity to add in stronger multi-factor options, which also don't require the app developers to do anything. Because again, as far as the app is concerned, the app started the flow by sending the user away from the app, and eventually they were returned, and now they're logged in. So let's talk a little bit about how OAuth works by looking at the actual building blocks under the hood. OAuth 2 is actually made up of a bunch of different specs, a bunch of different components, starting with the OAuth 2 core specification. This specification is the foundation of everything else, where it starts out by describing several different what are called grant types, which are different ways an application can get an access token to access data. One of the things that the OAuth core spec does not describe is actually what access tokens are or how they work. In the beginning, in the origin of OAuth 2, there was a pretty large debate about how this should work. And one of the ones that won out, essentially, was the idea of a bearer token, which is if you have the token, you can use it. The token can be any format. It doesn't have to be a particular string, a particular style of string. It doesn't have to be a JSON web token, but it can. The thing that makes it a bearer token is that if you're holding it, you can then present it to an API and use it. And if somebody steals it, they can use it just as well. Kind of going back to that hotel key analogy, same idea. Anybody who's holding the hotel key can use the door. This was a pretty controversial topic at the time because OAuth 1 did not work that way. So what ended up happening is that this got split out into its own specification to describe bearer tokens. There was a competing specification that pretty much died out and nobody uses anymore. We're going to come back to this point later in this presentation because this is an important point, and it's the foundation of a lot of the ongoing work. So what else is in OAuth 2 core? Well, it turns out that OAuth 2 was also trying to solve the problem of being usable on mobile devices where OAuth 1 really wasn't. And mobile devices and JavaScript apps were relatively new at the time that OAuth 2 was being created. So this was part of the design goals, but there also weren't quite the right tools available to do this really well. So what we ended up with was the implicit flow as a sort of band-aid for how to use OAuth 2 in a way that could be used in JavaScript, even if it wasn't necessarily the most secure option. The key thing that is the problem with the implicit flow is how it sends the access token back to the application. And that is by sending it in the actual address bar in the redirect. That's called the front channel. Anytime two things send data by sending data around over the address bar instead of making an HTTP request, that's the front channel. I like to think of this as sort of putting your message in an envelope and then sending it in the mail and hoping it makes it to the destination. There isn't really any assurance that that letter is going to be delivered, and on the receiving end, you don't actually know if the message that was delivered was from the real sender. And this is an inherent problem with using the front channel in any way. The particular problem with using the front channel for the implicit flow is that it's the access token sent in the envelope, which would be like sending your hotel key in the mail where you don't really know if it's going to get to the destination and you don't know if it's the real key when it arrives. So the implicit flow was used in JavaScript apps pretty commonly, but very quickly for the mobile world, it was realized that it was even worse using it in mobile compared to in JavaScript. So a new solution was developed called Parecki, which was meant to address the ability to use the authorization code without a client secret for mobile apps. We're not going to get into the details of how Parecki works. I'll save that for other videos. But there's a new spec, Parecki, and then there's another one after that, which is a recommendation for how to securely do OAuth in mobile devices, along with a bunch of other recommendations. One of the things it says is to do Parecki for mobile apps. Now, even later than that was another spec sort of parallel to the one for mobile apps for single-page apps, which is recommendations for how browsers can do OAuth securely. One of the things that's happened since the beginning of OAuth is that older browsers are no longer relevant, and now we do have things like cross-origin resource sharing, which essentially lets us use the authorization code flow with Parecki from JavaScript, which is super cool. It's great. It's the most secure way to do an OAuth flow from JavaScript. And what that means is that the implicit flow doesn't really have any use anymore. There's no reason for it. So the single page app recommendation spec actually says, don't use the implicit flow anymore. We have Parecki and cores is good enough. The security best current practice is yet another spec being worked on, still in progress, and that has recommendations for all kinds of apps using OAuth. And it goes so far as to say, don't use the implicit flow. It has no purpose anymore. Also, don't use the password flow because of what we talked about in the beginning, where it's a terrible idea for third-party apps, but even for first-party apps, it's very limiting and doesn't give you the ability to add in multi-factor and still has a couple of inherent risks as well. It also recommends using Pixie even for confidential clients that have a client secret, because it turns out there's even a particular attack that Pixie solves even if you still have a client secret. So even though Pixie was originally created for mobile apps, it turns out it's applicable to every kind of application, and it's always a good idea to use it. The security BCP also has a bunch of other recommendations, including, for example, don't send access tokens in query strings. So by now you're probably thinking, wow, this seems like a lot of specs. This is a lot going on. And yeah, you're right. It is. There's a lot to it. There's a lot of documents to read. And in order to actually get the picture of how to do OAuth securely, you have to read a bunch of stuff. But if you look at what's being described at the end of reading all of that, this is kind of what you get, which is actually a much simpler picture. Essentially, use the authorization code flow with Pixie, regardless of what kind of app you're building. Client credentials is still fine. There's nothing wrong with that if that suits your use case. And then there's a couple different ways to use access tokens in HTTP requests, and bearer tokens are just how everybody does this anyway right now, so let's pull it into the core. And this is really what OAuth 2.1 is. OAuth 2.1 is meant to be a consolidation of all of the current best practices of OAuth 2, kind of giving it a name, snapshotting it in time, and saying, when we talk about OAuth, this is what we mean. We don't mean original OAuth plus all the old stuff that nobody does anymore. So it's really meant to be a consolidation of all the OAuth 2 specs, adding in the best practices, removing the deprecated stuff, capturing it under a name that we can use to refer to the best practices of OAuth. One of the other things doing an update lets us do is there's actually a lot of stuff in the original draft that is either missing because extensions weren't defined yet, or it's references to other specs that have been updated and those references are now out of date. So we're able to update all those references, add in references to extensions that didn't exist when OAuth was created, and really help people get a new idea about what modern OAuth actually means. Along those lines, things we're not doing with OAuth 2.1 is it's not actually defining new behavior, which essentially means if you're doing OAuth 2.0 today in the way that is considered the best practice, you're already doing OAuth 2.1. So ideally, it's not a lot of work to upgrade to OAuth 2.1 because hopefully you're already following the best practices. This does mean that OAuth 2.1 is not getting updated with any sort of newer or experimental or not widely implemented features yet. You can find more information about OAuth 2.1 at the links on the screen. Now what I want to talk about is some of the more recent work that goes beyond OAuth 2.1 and stuff that is new extensions being developed by the group and experimental stuff. We'll start with a couple of recently published OAuth extensions. These are recent RFCs that have been gone through the whole process and now have an RFC number. We'll start with JSON Web Tokens for access tokens. In OAuth, access tokens can be any format, and in practice, a lot of people have a lot of different ideas of how access tokens should work, which is fine. Because it turns out most people don't need access tokens to be interoperable other than between their own API and their authorization server. However, if you are building a product that is a standalone OAuth server like any of the open source ones or Okta or Auth0, then those are going to be used by a lot of different resource servers built by different people. And those people are going to be using libraries. And that's where it would help to have a standardized format for what access tokens actually look like. So JSON Web Token profile for access tokens describes how to use a JSON Web Token as an access token, mainly for the authorization servers to implement. It describes what things to put into the claims, what kind of algorithms to use to sign it, how that sort of structure should work, and it tells resource servers how to validate these as well. Push authorization requests is one of my favorite ones that's now recently published. This kind of flips the OAuth flow on its head. In the traditional authorization code flow, the client starts out by building a URL to the authorization server, and then sending that URL through the front channel so that the browser makes that request. Again, anytime we're using the front channel, we have to think about putting that message in an envelope and sending it in the mail. So what we've done is the client's built a request including things like what scopes it's trying to access and what redirect URL to use. All that stuff is sent in the front channel, which means it can be observed, but more importantly, modified by the user. So what push authorization request does is it actually starts the flow by sending all that information in the back channel. It sends it in a post request up to the OAuth server and gets back an opaque identifier to start the flow. That means it can send things that is not visible to the user, because if the app is running on a web server, that's server-to-server communications. This is kind of what it looks like. Instead of the GET request to the authorization endpoint that the browser makes, instead the client first makes a post request to the new push authorization request endpoint with all of that same data that would have been in the GET request. And that is then able to be transmitted securely in the back channel so that the user can't modify it. Also along those lines, solving a similar problem is the idea of using a JSON web token to make that first authorization request. So again, instead of putting a bunch of query string parameters into the URL, the client would first create a JSON web token with all of that data in it, and then pack it up, sign it, and include that in the URL. There's actually a few different ways the client could send that to the OAuth server. One is in the URL, one is by reference to that record existing at some other URL, or combining it with push authorization requests and posting it to the endpoint as well. These two things combined are the most secure. Now I want to talk about some of the in-progress or more experimental stuff. So I mentioned at the beginning that bearer tokens are the most common way access tokens exist right now. And that just means, again, that anybody that has a token can use it. So if you can steal a token, you can use the token. We would ideally like that to not be true. And that's the idea of sender constraining the access token. Right now, if you can find a token, you can use it and you look like the real client that's supposed to be using it. So what we're looking for is some sort of authentication of the client instance in order to use the access token. Emphasis on the some sort of and client instance sort of hand-wavy bits here. Basically what it means is that if you were to get a hotel key, ideally, when you go to the door, only you can use it, and if you dropped it on the ground, somebody else wouldn't be able to pick it up. So how that actually ends up working in practice is currently up for debate. There's a lot of different options and a lot of different attempts at solving this over the years. Here's a handful of specs that have been attempted to solve this problem. The only one that is an RFC status is mutual TLS. This is fine, it works in practice, a lot of people are using it, but it is challenging to deploy in certain scenarios, depending on how you're doing things like load balancers or API gateways. So there is clearly a need for an alternative to mutual TLS, which is the very experimental part that's happening right now. Of the remaining 4, it's really only the top 2 that are currently active and being worked on. The other ones kind of died out for various reasons. So we have Depop and signed HTTP requests. Depop solves the problem by doing all of that sort of proof of possession and public-private key stuff in the application layer, meaning your OAuth client would be where that code lives. Signed HTTP requests, on the other hand, does that at the HTTP layer, meaning it's your HTTP client that does that. So think like how you can tell curl to just add a header, you would be able to tell curl to sign a request. Whereas doing it with Depop would mean you're writing into your OAuth client how to do this stuff. Here's a quick snapshot of what they look like. Depop is the idea of signing the different parts of your message and then building up a token and including that in a header in the HTTP request. HTTP signatures has a way to select which parts of the message you want to sign and then including that signature in the request. The HTTP signatures is useful outside of OAuth and it can be used for anything, any sort of HTTP message, but the OAuth application of it would then tell you which headers to sign. Both of these are very much still in progress. There's a lot of interesting discussions going on in the community right now. So this is actively in progress if you're curious about joining the discussions. There's a couple other new OAuth extensions that are also in progress. Rich authorization requests is a very cool idea for essentially taking the idea of scope and letting that express more detail. So where scope is able to say things like, this app wants to access your photos or it wants to read your email, you can't really do things like, this app wants to move $10 from this account to this account, or this app wants to pay this merchant a certain amount. That's not able to be expressed by OAuth scopes. So what Rich Authorization Request does is it defines a framework for being able to build those kinds of requests. It defines a JSON structure and how an application and authorization server can create these requests to describe fine-grained authorization. Authorization server issuer identification. This one's actually a really small spec, and because of that, it's actually almost finished going through the RFC process already. Basically, there is a mix-up attack possible if a client talks to multiple authorization servers. It's a relatively simple mechanism that clients and servers can implement to solve it, so it is pretty straightforward, and I expect to see adoption of it for scenarios where a client is using more than one authorization server. JSON Web Token response for OAuth token introspection. So normally the token introspection response just returns you JSON data. It just returns a bunch of properties about the token. The JSON Web Token response spec says, actually, if you want to, the authorization server can reply back with a full signed JSON Web Token. The cool thing this does is it actually lets the resource server write this JSON Web Token to a log file, which means it can then prove, because the signature matches, it can prove that the OAuth server did in fact reply with that data. Otherwise, with the plain introspection response, the resource server can't really prove anything. So what about the future stuff? Is there an OAuth 3? You may have heard some rumblings about it. Turns out it does not exist. There is no such thing as OAuth 3 right now. The working group is working on OAuth 2.1, and there is no current effort to create an OAuth 3. However, there is a different group working on something that used to be called TXauth, XYZ, and is now called GNAP. That's an emulation of all the different flows of clients needing to be pre-registered and getting around the limits that ends up sort of putting in place in the rest of the OAuth flows. Proof of possession and asymmetric cryptography are also baked in in the core spec. So if you're curious about that, there's a lot more to learn there. It's also very much in progress and is nowhere near being done and is unlikely to be actually usable in commercial products anytime soon. Lastly, I want to wrap up with some resources for where you can go to learn more. The OAuth Playground at oauth.com/playground. This is a great place to try out and see a demo of all the flows. It's basically an emulation of all the different flows. I have a video course that talks about OAuth. It goes into all of this stuff in a lot more detail. You can find it at that link, oauth2simplified.com/course. On oauth2simplified.com, you can find copies of the book I wrote, as well as stickers of the cats and of the OAuth logo if you want. You can also read the book online for free at oauth.com. It's available there in its entirety. It's a free resource. It's laid out as a web page, and you can browse and search it. Thank you. That's all I have for this. I hope this has been fun. It's been quite a whirlwind. There's a lot going on. There's a lot to learn, and there's a lot of new ways to get involved if you're interested in participating in the development of OAuth. So take a look at the links below, and thank you all for this. It was a lot of fun, and have a great rest of the conference.
Yeah, thank you, Aaron, remotely.